All right, guys, welcome back. So today we want to talk about memory system finally and caches. Does anybody have any questions about things in the past, homework, quiz? All right. So before we get into the cache, very quickly, I want to summarize what we described and discussed last week, and then also add a few important notes to what we discussed. Essentially, we talked about out of order execution, the challenges and the new things that we need to add to our out of order execution machine. Three things that we kind of added was, one mechanism for finding, what is ready and what is not ready, and then fixing the forwarding and raw data hazard issue. Then we said that essentially out of order creates a new set of issues and hazards, including write after write and write after read. So we introduced renaming to fix that. And finally, we said that there is a whole bunch of issues because of out of order execution caused by things like branch misprediction and any sort of misprediction because of a speculation that we use. And for that, we introduced the notion of ROBs, right? So we introduced the notion of dispatching and renaming. We introduced the issue of the concept of reorder buffer and retiring, scheduling and reservation station, and we said that essentially we are combining our ALU and memory into what we call a functional unit, and functional units could be multiple of same kind, or it could be different kind, and so on and so forth. And we introduced, the week prior, we introduced the notion of superscalar, which we essentially copied the pipeline or a data path into multiple instances. Okay. There are a few challenges that last time I said that we're going to talk about this in this lecture. For the first 15-20 minutes of the lecture, I want to talk about those, and then we're going to move on to the next topic. So things that you might ask yourself when we discuss out of order was, like, for example, what the recovery looked like, right? So we talked about, okay, there's an ROB and we're going to go through the ROB. But there's more details to it that we want to very quickly go over them. So these are very, complicated and very detailed, topics, and require, a separate course for it. But what I would do now is just, just give you a generic idea of each one. We don't want to go through the details as the way that we did for example, pipelining, because unfortunately we don't have time. But maybe if you're interested, you can always take, an advanced course in computer architecture and go through these, or read the book and so on and so forth. Okay. And these things I won't ask question in the details of this won't be asked in your quiz. Okay. So one first basic thing that we need to consider is essentially what we can do is when we have our reservation station and ROB, there are two kind of train of thoughts or school of thoughts. And one is saying that, okay, what we can do is we can have what we call a centralized ROB, which essentially we just park everything into the ROB and we use that as our reservation station as well. And the other idea is what we kind of discussed in the class, which we have a separate unit for our reservation station. Then we had our functional units, and then things go inside the ROB. But in many systems, including many of the Intel processors, instead of having a system like this, what they do is basically the renaming goes into the ROB plus reservation station in some sense. And the functional units, have their values, and this values goes back into the ROB. The nice thing about this is that then everything is kind of done internally. Okay. So, and then the queues are kind of unified, and you might save lots of space. But on the other hand, the complexity of designing that becomes more challenging. Okay. So what we discussed in the class was this design, but keep in mind that this is also very common and widely used in different microarchitectures. The second thing about renaming, what we discussed in the class was, we can use a register alias table, and we go through that table and we kind of like, find the next, free pool, and then find the mapping between the architectural and physical registers. Another idea that also widely used is the notion of tagging and use tags. So what does it do is essentially assign a tag for each architectural register. So there is no like a mapping between an architectural register and physical register. All it does is basically saying that, okay, X1, for example, has this tag number 1. The next time I see X1, I assign a new tag to it, T2, and so on and so forth. So basically, our tags is kind of like, instead of using the actual physical register, we use these tags. And the nice thing about these tags is then we can broadcast them, we can get rid of them, we can use them, and so on and so forth. And this is also completely eliminate the need for a RAT, because what the processor can do is just basically using this one-time tags for every single one of these architectural registers. And once the instruction is retired, just get rid of the tag and move forward and so on. So all we need is really a counter that's kind of like keep track of the tags, right? And then if you want to write to that register, all we need to do is find what tag this is. We broadcast that tag, and then if tag matches, then the value gets updated in the reservation station. Question. What does RAT stand for? So RAT is register alias table. Okay. So this is, if you look back at the notes in the book or other resources, you will probably see this famous algorithm, Tomasulo's algorithm. So this is basically one way of doing out of order execution. It's basically based on tags. Initial processors are usually using these tag systems. Still, there are some modern systems that use that. What we did in the class, though, was basically using an alias table. Question. So the question is, what is the difference between the tag system and using a RAT? So RAT is essentially a table, right? And what we do is basically just using physical register throughout our data path, right? Tag is kind of like saying that, okay, we don't need a table. All we need to do is like having a counter starting from 0. Whenever we see a destination register, whenever we see a register, we assign a new tag to it, okay? And then we have an initial mapping of those tags, and then as we move forward, we just use those tags. We never actually need to go through a table to read that and go to the free pool and do that. All we need to do is just assign a tag, which could be done very, very easily. The problem with that is, keeping track of the tags and storing tags might be more expensive, because you might need like, longer tags and so on and so forth. But it's just, again, it's just very similar to what we did, slightly different way of thinking about it. So instead of like actually translating it to a physical register, you can keep it in the architectural stage, but using tags for doing things. Okay. The another question is what we showed in the class and in the example was that we had our reservation station, and we said that basically we have data and we have the readiness for each unit, right? So for example, we say this is RS1, this is the value that it stores, and this is the ready bit for example, RS1. So we basically go through our register file during the dispatch state and actually read that register and put it into our reservation station, right? The other option that we can do is that instead of saving this file, in the register file, we just store either the tag or the register number. And when we want to, from dispatch go into the fire station or the issue station, when we are actually, transitioning from this cycle to that cycle, this is where we actually read the register file, okay? So the register file reading happens during the execution and not during the dispatch state. And the advantage of this approach is that we don't need to store things in our reservation station. The second thing is that forwarding becomes much more easier, because forwarding in the method that I described, has to happen that, the execution is done. We go to the complete stage, and complete needs to kind of like, put feedback back to the reservation station and update the values in our reservation station, right? Whereas this approach, what it says is all I need to do is just basically, in my register file is just, adding the muxes and then, mux through the values. So basically, essentially the same way that we did in our pipeline design. Remember, in pipeline design, what we did was during the decode stage, we had a register file and we read RS1 and RS2. But we said that essentially, when we are going to the pipeline register and we read these two values are garbage because it's an old value. So what we did was we added this muxes here, and then we kind of forward back from later stages to the execution stage. Okay, so you can use the same idea here. So instead of actually updating your reservation station when the complete happens, you can just not store things in your reservation station and then just forward things into your issue stage. Okay, again, we didn't do that in our example, but that's also a very common way of doing that. The pros and cons on each one is like, if you're doing this, then you need to deal with, control signals here for your muxes. You need to add more muxes, and there is like, complexity associated with that. But the good thing about it is that you won't have timing issues potentially in your reservation station, and the design of your reservation station just becomes much more easier. Okay, so this is like the trade-off between these two approaches. So this is kind of like, also relevant to the idea that we had there. When to forward, we also discussed this, and we said that essentially when we are forwarding is when the instruction is complete, right? And this means that, we need ports from our ROB, we need ports from our complete stage to kind of like, forward it back. Well, one thing you can do is that you can say, okay, what I'm going to do is I can wait until the instruction to retire, and then I can do forwarding. And this makes things much more simpler because you don't need you don't need extra ports, you don't need the mux. You just write things to your register file and read from the register file. So this is kind of like similar to the idea of stalling the processor, right? Because basically saying that instead of forwarding, we stall the processor, we wait for the register file to get updated, and then we read that, and there is no issue, nothing you need to do, right? The good thing about this is that it makes the design simpler. And for out of order execution, this usually doesn't end up being stalling. All you need to do is just park those instructions more into your reservation station, because now we have multiple different instructions in our reservation station. Maybe this one is waiting for that register, but all these others can be actually going to my functional units, right? So unlike the in order case where I had to stall the processor until the value goes into the write back and actually written to the register file, for out of order, I probably can find other candidates and I can push those into my functional units and complete and retire stage, and hopefully the other instruction comes back and I can do it. So in terms of performance hits, there will be some slowdown, but the slowdown wouldn't be as significant as what we did for stalling and not doing the forwarding for in order. So for in order, we definitely need forwarding, but for out of order, we can tolerate not having forwarding in some cases. Okay. Another thing to consider is what exactly is happening during the flush. So there are lots of things that needs to be happen during the flush. We talked a bunch of it, but let's go through the actual things that needs to happen. So we need flush things from our reservation station. We need to remove those instructions from ROB. We need to restore our register alias table because there were some renaming for new instructions, and all of those are kind of invalid renaming. So we need to kind of revert them back to what they were before the renaming. Since we are restoring the RAT, we also need to, free those new registers that we kind of assign We need to free functional units that for those instructions that are invalid instructions. And we need to update the PC. We need to find the correct PC, and then we need to update the PC. So there are lots of things much more complex than what we did for in-order processors. Essentially, all we say here is that whatever steps that we took when we are, reading one instruction and putting it into our renaming and reservation station and ROB, you just need to step by step revert all of those back. And now you can see why for example, we keep track of the old register, why we store things in our ROB and reservation station and so on. So all of these things are for the scenario that we see that we made a mistake, and then we need to kind of go back and fix that issue. Okay, any question here? So there are two ways of recovering things, and this is mainly for performance purposes. So in order to restore things, the way that we kind of discussed it in the class with all those additional units in reservation station and ROB is what we call a log-based approach, which we keep track of logs of old things and we save those into our RAT, into our RS, into our ROB, and then when something happens, we just go and read those logs and kind of replace those logs with the current values, right? So what we did was kind of this. But what we can do instead is we can do what we call a checkpointing mechanism, where we're going to say that we're going to replicate everything once. So I'm going to have an RS or register file, and we're going to have what I call a messy register file or messy RS. And what this messy RS is that I don't care about out of order execution and the fact that I need to recover things. I just write things to my register file, just updating everything, write things out of order and whatever it is. Okay, so I'm just pretend that there is not going to be any flush in future, and then I'm going to have what we call a clean register file. So this is our original register file, which is clean. And this one is basically keep track of things in the right way. And then we're going to have a mechanism that after a while, when things are safe, then we are basically right from messy to our clean. So we are saying that, okay, what I'm going to do is that I'm not going to worry about all these things for recovering. I'm just going to keep writing to my messy register file and messy reservation station and so on. And if something happens, then I always have my checkpoint of clean, and I'm going to copy things from my clean to my messy, and nothing bad happens. If nothing happens, then at some point I can copy things from my messy to the clean and create a new checkpoint, right? So I'll say, okay, I'm gonna if there is no branch here, then there is no way that this instruction is gonna get this list of instructions is going to get flushed. So whenever I reach to a branch, what I can do is that creating a new checkpoint. I'm going to copy things from my messy to my clean. This is my new clean. This is my new checkpoint. From this point that I have a branch, I'm just going to carelessly update my messy, but I'm not going to touch my clean register file. And then if something bad happens, I can always copy from my clean to my messy. If nothing bad happens, then I can just continue, create a new checkpoint from messy to clean and move on. And the interesting thing about this is that we are kind of, put the recovery phase into kind of a background. We take it out of our critical path, and our performance significantly improves because we essentially just treat this as a regular in-order processor. We just write things to my register file and so on. So I don't need to deal with the forwarding and all those things in many cases, because I can just whenever the instruction is finished, I can just write it directly into my register. Yeah.
So do we update checkpoints right before we reach register?
So the question is that when do we update the checkpoints? Yes, usually. So I mean, again, there are details to it, but what we do is that if there is any speculation, we need to update our checkpoint. And we can think about it, this could be a branch. Nice, good question. The question is, what if we have multiple branches? Then you might need to do multiple of that, or at least at some point you need to kind of, in your messy, you also need to, do something. But that's exactly the problem with this approach, that at some point you cannot go further down. There are multiple ways of checkpoint. So what you can do is that, okay, so if I have two branches, I'm going to create a checkpoint here. I'm going to create a checkpoint here as well. And then start executing instruction. If I decided that I need to recover here, I'm going to go through this checkpoint. If I see, no, I made a mistake here, I'm going to go through this checkpoint. So I can have multiple checkpoints and then just refer to them as much as I need. But there is unfortunately a limit to it. Correct. The question is, you're checkpointing the registers that are changing. Yes, both that and my memory, because if I write things to my memory, but you only save what is called a delta. So you don't need to store everything. You just store those things that have been changed. Okay. So the amount of things that you actually store is significantly less than the entire memory. You don't need to store the entire memory. You just change those lines that have been changed. We also talked about hazards. We said that essentially our raw data hazards is that ready bits that we use in the reservation station. The control hazard is when we have, for example, the ROB or our RS full, right? So what we do is, if the instruction, if the lines get full, we need to stall the processor. We need to stall the decode and fetch state, and then we need to continue the dispatch, the execution or issue unit are complete and are on our retirement stage, right? So we basically stall the fetch and decode, and then we continue everything else. And then the structure, sorry, this was for structural hazards. And for control hazards is when we have a speculation, right? And then we extensively talk about that, right? We have either our checkpointing plus messy clean strategy, or we have our regular ROB and RAT and all those things. Okay, so we basically can handle all these different hazards that we talked about. The structural one is when there is not enough units, and for that we are basically using stalling plus cleaning up our ROB and our reservation station. For control flow hazards, we are using ROB and the concept of retiring instructions. Interestingly, there's a new type of hazards that happens in out of order execution, and that's what's called a memory dependency. So the memory dependency is actually exactly all those things that we discussed in the class for registers, but this time for memory. For example, let's take a look at this example here, that I'm storing 0 plus storing whatever's value x1 has in the address that points by x2, and then another instruction that we are doing is I'm storing whatever x3 has into whatever address that x4 is pointing to. And the interesting question is, what will happen if x4 and x2 are equal to each other, right? If x2 and x4 are equal to each other, what will happen is that we are basically storing into the same address. And if x1 and x3 are not equal to each other, then we will have the same write after write hazard that we discussed for registers, right? And if we, for example, execute this first and execute this second, that is a correctness issue, because we are assuming that we are storing specific value into our memory, but what we are storing is actually the other way around of what we assume, right? So it's very similar to what we had for registers of write after write, but what happens here is a tricky way of this write after write, because the addresses are the same. We will have this issue. And quickly someone might ask that, okay, why are we not using renaming for this, and why is this a problem? Because the renaming doesn't help here, right? Because first of all, there's nothing to rename here, and the second is we are talking about addresses. We are not talking about the registers. We are talking about the potential addresses. So in order to be able to rename, we need to know what is the value of x2 and what is the value of x4, and then if these two are the same, then we need to kind of like fix this issue, right? So the problem with memory dependency and memory hazards is much, much more complex than register hazards, right? And you can have this same issue with raw data hazards, and you can have it for write after read data hazards. All of them are essentially, the idea is that you're using a register to address the memory, but those addresses end up being the same for both cases. Okay, is that clear why we have a hazard here? Okay. So, and then the problem is that the renaming won't fix it because we don't know the addresses, and the changing the register doesn't help here. Okay. So what are we doing to help to fix this? We're going to introduce the notion of what we call store queue. Okay. So the store queue is literally this queue that, think about it, similar to ROB, but for store instructions. So what we're going to do is that whenever we have a store, instead of directly writing it to my memory, I'm going to write it into this store queue. And then after the instruction gets retired, then I'm going to write from the store queue into my memory. This way, I'm going to ensure that this writes will happen in order, right? If I write into the store queue in an in order fashion, or even out of order fashion, if I store their PCs, and then just whenever the instruction gets retired, I just write into the memory, I'm guaranteeing that this writes to the memory will happen in order, because the retire happens in order. Since retire happens in order, this writes to the memory also happens in order, right? So I'm kind of like adding an intermediate stage into writing to the memory by writing to my store queues first, and then whenever the instruction gets retired, then I'm going to write it into the memory, okay? And this way, we are kind of fixing the issue of writes after writes, because then even if you have multiple writes after each other, the writes actually happen in order into our memory, right? Is there any question here? Cool. But the problem of raw data hazard doesn't fix here, because raw data hazard is when you have a load after store, and if the load happens before the store, then we're going to have a raw data hazard. So how do we fix that? We fix that by adding a notion of load store queues instead of having just store queues. So we call it LS queues. So what we're going to do is we will have a table like this, that for every load and every store, we're going to first go into this queue, and we're going to search through this queue and then get the value that we want. If the value is not in the queue, then we're going to go to our memory. So what happens for load is, if we have a raw data hazard, we're going to have a store, and we're going to put that store into this queue as I described earlier. Then we're going to have a load, and this load, what will happen is that instead of like originally going to the memory and trying to read the old value, the load will go into my store queue and then search through the store queue to see whether there is a match between the address of the load and any of the entries in my load store queue. If there is a match, then basically this load store queue acts as a forwarding unit for us. So it's not reading from here, it's actually reading from here. So this way, if I have a raw data, if I have a store and then a load, what I will do is the store will be in my queue, and when the load comes in, it will go through that queue and see that value, and then it updates that value from the queue. Okay. So again, this trick is basically we are reading and writing from memory. We don't do it right away. We just put it into our store queue. When the actual retire happens, that's when we actually execute that instruction. And during that time, it is guaranteed that that instruction is happening in order. And since this is happening in order, we are guaranteed that there won't be any raw data hazard or write after write data hazard or write after read data hazard, as long as we keep track of things into this load store queue. Does that make sense? Yeah. So we have, so let's see what's the question. So multiple stores and a load. So we have store, store, and load like this. Okay. So we're going to put this into our LSQ. We're going to put this in LSQ and put this in also LSQ. And they won't be executed until first this one retires, then this one retires, and this one retires. So first this one retires and we update the value in my memory. Then this one retires and I'm gonna re-update the same value in my memory. Then this one wants to get retire, and this one can then go into either reads the forward the value from this, or just goes through the memory and bring the value up from the memory. And in both cases, it's always guaranteed that it's going to read it from the second store. Does that make sense? So basically, the trick here is that, yes, these stores and loads in the original execution might happen out of order, but we're going to put them similar way that we put things in our ROB. We'll put them in LSQ, and we don't really execute them. We don't really read those value until the retire command comes in. And since the retire is happening in order, then it's guaranteed that this stores and loads happens in order. That's the kind of like the high level idea of why this would work. Does that make sense? And then another nice thing about this is kind of like save us a lot of time, because again, this kind of acts as a forwarding unit for us. So instead of all the loads goes all the way into the memory and read things and bring it back, the store queues is like a small buffer sits between the processor and the memory, can actually forward the values for us, right? So we basically our actual load is actually a read from this load store queue, which is much more faster than the memory itself. So it also has this added benefit, okay? And then there's going to be a problem with the load store queue, and that is that what if the load store queue gets full? Then what should we do? Then we have to stall the processor to make sure that this load store queues first gets emptied, and then we can continue. Because if the load store queue gets full, then we cannot issue new loads or stores, right? So we need to stall those stall those instructions until these things are written back to the memory. Then we have new entries in my load store queue, and then I can continue. Okay. All right, so that's kind of it with the out of order execution. We are basically right into kind of like the state of the art. All the optimization mainly that we talked about for a processor. If you look way back in lecture 0, when I was talking about the timeline, now we are kind of at around like 2003 to 2005, when we had this best performing single core processors that was like very performant, about 25% per year improvement in performance and so on. So we are at that stage right now with all these things that we mentioned. Of course, there were some details that we didn't have time to go through, especially about out of order execution, but I think we have a general idea of how a modern processor works. And the architecture these days is kind of pretty much the same as what we discussed now. So it really hasn't been significant improvement. It's like fundamentally changing things. It's basically some smaller tricks that we use these days to make these things faster. Okay. So now it's instead of like jumping into what happens after 2005, there is a parallel trend with the processor that happens throughout that time, and that was the memory. If you think about what we discussed earlier at the beginning of this class, we said that basically our model of a computer is a processor or a CPU which has a data path and a controller, and this CPU is actually talking to a memory that we also, so far we treated it as an instruction memory and data memory. And we said that essentially things are stored there, and the CPU goes there and read things and bring it to the CPU. And then we talked about all these optimizations in order to make the CPU faster, right? So let's talk a little bit more about memory, and that would be the discussion of this week and next week, and maybe a little bit of the week after. Then we're going to move back to our timeline, and then we're going to talk about what happens after 2005 and what we have right now is like, the most recent systems. Okay. To understand why memory is important is to look back at the trend that we discussed in the class. And what is really, really happening is what we call a memory wall. So if you remember, I told you that, the speed of, increasing the speed of the processor was like, following the Moore's law. And we kind of like doubled the number of transistors and improved the performance by 25% per year, or like, twice every 2 years, or so on and so forth, right? Unfortunately, what happens is that for the memory, since it's completely different, VLSI technology, the improvement speed is about like only 7% per year. Okay. And as we are moving more toward, current time, there is a huge performance gap, about 50% per year, year after year, between the improvement in performance of the memory and the improvement in performance of the processor. And this is what we refer to the performance gap or the memory wall, because our processor is getting faster and faster, but our memory is not getting faster. And the problem with that is, if you remember, we need to fetch one instruction at a time, right? And then there are some data memory, and then like, load and store things that needs to happen. So if these things start to get really, really slow, then our entire pipeline gets slow, because we need to stall the processor, wait for this data to come, and then continue. And then if this time doesn't really scale, then it doesn't matter how fast the rest of the processor is, because this is the bottleneck of our system, right? So if you want to really get performance out of the system, we need to think about what we can do for the memory as well, and how we can make the memory fast as well. Otherwise, we're not going to get anywhere. We're just going to make something really, really powerful, but the second thing would be very, very slow. Okay. So that's the kind of like, what we want to talk about. So like how to fix this memory wall problem, and what the computer architect can do to kind of mitigate this issue. Okay. And in order to understand that, the first thing that you need to know about the memory is, unfortunately, the memory is either large or either fast. But what we want to have is a fast memory that is also large, right? Fundamentally, because of the technology that we use, memory cannot be fast and large at the same time. But what we really want from the processor side of view and for performance side of view is that you want a memory that is both large and both fast. Okay. So what we do to fix this issue, that's where the whole idea of memory hierarchy comes into play. So what we say is, let's, instead of like having this one large but slow memory, having tiers of memory, let's call M1, M2, and M3, that what they do is the first one is slow, but as I say, slow means fast. The last one is large, but large means slow. And what I'm going to do is that I'm going to intelligently move data around these units from the processor side, we get this illusion that we have the size of this, but the speed of this, right? So if you are very, very smart about the way that we are handling and moving data, about how we manage our memory system, we might create this illusion that the CPU interacts with very large memory, but this memory is also very, very fast. And the trick is we basically move data around internally between these stages, this units, that some of them are small and they're really, really fast. So they're fast enough to talk very fast with the processor, but they cannot store everything that we want. So we kind of like, move things around with some tricks in order to create this illusion. Okay, and that's the concept of memory hierarchy, and that's what we want to talk about in this lecture and the next few lectures. So the first question is, why would hierarchy work? Like, why this essentially actually a good idea at first, and then we're going to talk about the details of how we implement this idea. I already gave you this example, but let's actually revisit this example. And that's the analogy that we use with the libraries. And you will see that actually hierarchy is something that we use in our everyday life without actually knowing that this is actually the concept that we very extensively use in our computers. So instead of thinking about data, think about books. And what we want is to access any book that we want as fast as we want, right? So we are the processor, and the books are the blocks in the memory, okay? So in this analogy, the current book that you're reading would be the current data that the processor is dealing with. So the data that's been read from the memory into the processor. And then what you will do is you probably use your frequently used books into a desk near you. So such that, if you, extend your arm, then you can quickly grab the next book and so on, right? So the time it takes for you to read a book, change a book, is just like, a few seconds or few even milliseconds to just change this book that you're reading, put it back and bring in another book up, right? But the problem is that your desk has only can supply a few books, right? So maybe 5 or 10, depending on what's the size of your book, your books are or your desk are, right? So what you would do is that adding another layer of hierarchy to your example, and then you have a shelf in your room which you also store some of your books there. So you will have one book at hand, bunch of books on the desk. And then for those books that you probably read less frequently, you put them in your shelf. And this story basically continues. Then you probably have another larger shelf or a box in the attic or in the garage or somewhere else. And then not only that, there's also the option of going to actual library or the bookstore and grab the book if you want to. But if you think about this hierarchy, what happens is, starting from the book that you're reading, you have zero latency access to that book. You have a few second access to books that you have in your desk, maybe a minute for the books in the library in your shelf, maybe 15 minutes or 30 minutes to the books that you have in the attic, and maybe in an hour or so for the library, and so on and so forth, right? So if you think about this, that all of these data is still accessible, so you technically can access all the books in the world. It just takes different amount of time for you to read those. And what you need to do is, understanding this limitation, you need to come up with an idea and a strategy that say, okay, if I have an exam this week about this course, it's wise that I put this book into my desk. And if there is an old course that I no longer need that book, I either put it in my library, or if my library is full, I'm going to put it in the attic. If my attic is full, I'm going to just get rid of it. And if I need it ever again, I'm just going to go and buy it or borrow it and so on, right? So what you would do is that based on demand, you're going to organize the storage of data. And that's exactly happens in the cache and in the memory hierarchy. Things that I need most, I keep it closer to myself as the processor. Things that I need less and less frequently, I put it as far as possible. In memory analogy, that would be the disk. I put everything into the disk. And then if also disk is not full, then I put it in the cloud. I put it somewhere else in the world, and then I just can access it if I want. Okay? So that's the idea of the hierarchy. Another thing that is useful for hierarchy that's kind of makes sense is that for book analogy, the reason that we kind of decide what book to use and what book not to use is basically based off, for example, the courses that I'm having or the exams that I'm having and so on, right? In our processor analogy, this is what we call locality. I already talked about locality, but I told you that I'm going to talk more about locality when we get to the caches. So the locality is basically based on this principle that if you're accessing something there is a really, really good chance that we're gonna access the same thing in future, or we're gonna access something similar to that in future. The first one is called temporal locality, and the second one is called spatial locality. The temporal locality is that if I read this book or if I read this data, probably it's a good idea that I keep this data close to myself for some time, for some small window. And because it's very, very likely that I'm going to need this data again and again, okay? So what I'm going to do is that if I read something, I'm not going to put it back into the memory. I'm just going to keep it somewhere closer, okay? So that's the temporal locality. And the spatial locality says that if I read something, if I read this address in the memory, address X, it's very likely that I might do access X plus minus D, and D is a small value. So I might read X minus 1 or X plus 1 or X plus 2 and so on. And this is mainly because the way that we are writing our programs and the way we're writing our arrays, we usually read things from an array. We really like to read things from an array or a matrix. And matrices are these indexed from some base, right? So we are usually doing a base plus 1, plus 2, plus 3, plus 4, and so on and so forth. So the spatial locality is basically saying that, we can predict that we're going to use this kind of array-like behavior. So why don't we, when we are reading X1, maybe it's a good idea to also bring X2, because the act of going and bringing things takes much more time. So if you're going to your attic to bring this book, maybe also think about what other books that you're likely going to read and bring those as well with you, okay? And in processor analogy, this is spatial locality. This is address dependent. So if you're bringing address X, go and bring address X plus 1 and X plus 2 and X plus 3 and so on. Of course, you cannot bring all the things because you have only limited space, but maybe bring a small amount of data with you whenever you go and read your memory, okay? So this is the idea of the spatial locality. So basically combining these two, that's why the memory hierarchy will work, and it's actually worked really, really well. You will see at the end that we're going to have a significant performance boost just because we are, following this idea of memory hierarchy. Basically, the key idea of memory hierarchy is that bringing data that you're going to use as close as possible to you. And then the $1 million question becomes that, how do I know that? How do I have this vision of what data I'm going to use and how to bring it closer to myself? And that's the answer to that is what we're going to discuss in the next few slides. Okay. The final thing before I actually start to talk about that is you'll see this slide before early on. And we said that essentially we have different storage. And this is the underlying idea of having memory hierarchy. We said that we basically have our registers. Our registers are really, really fast, but very, very expensive. That's why inside our processors, we have a register file. And this register file is very small. We are talking about 128 registers, each 132 bits. So we're talking about few hundreds of bits. And that's really what we can afford in a processor. Then we will have what we call a static RAM or SRAM. SRAM is less expensive in terms of area compared to a register file, but it's also still relatively fast. It can provide data within few cycles. And that's what we're going to use for what we call caches that I'm going to describe later. And then we're going to have a bigger memories, our DRAM and disk. The DRAM is what we usually call as our main memory. The DRAM is much more, compact and less expensive than SRAM, but it's unfortunately much, much more slower. And then finally, we have our disk, which is basically our solid state drive or our flash drive. And this disk is really, really large. It's also non-volatile, which means that we don't need to power it on to keep the data, versus all these others are all volatile. and it's really, really cheap. So we can store terabytes of data within the same disk without being worried about the power and all those problems. Okay, so because of these different technologies, we have this arsenal, we have this set of tools to create this M1, M2, M3 that I showed you in this picture. That basically we're going to have our register file here. We're going to have our SRAM basically here, our DRAM here, and our disk here. So that would be basically the basis of creating our memory hierarchy with this. Okay. So to give you basic idea of the numbers, so for register file, we are talking about a few kilobytes, and we are talking about the access time of less than a cycle, right? We're talking about less than 1 nanosecond of time for reading register file. For SRAM, we are talking about hundreds of kilobytes. And typically, the access time depends on what size you're using. It could be somewhere between 2 to 10 cycles, which means it translates into 1 to 10 nanoseconds of access time for SRAMs. For DRAMs, you're talking about gigabytes of a DRAM, but you see the significant jump from 10 cycles to hundreds and hundreds of cycles, even thousands of cycles for DRAM. So there's a huge jump between SRAM and DRAM. And then there's even a bigger jump from disk from DRAM to disk. So for DRAM, it takes few hundred or 1,000 cycles to access. But for disk, we're talking about tens of thousands of cycles to access disk. But we're talking about terabytes of data that we can save. So if you actually look at the register file versus disk, you can read things from your register file within a cycle. But if you need the same data from your disk, it's going to take tens of thousand cycles to read the same data. And that's very, very important, because if you read most of your things from your SRAM and register file, then you will not notice the huge overhead, the latency overhead that you have in your main memory. But if you keep reading things from your disk, that's when your performance significantly hit, because you will see this problem that for reading every single value, it takes thousands and thousands of cycles. So if you notice, for example, your startup in your computer takes a lot of time, because that's when you're actually reading your information from your disk. But when your system's kind of warm up and you start using it, you'll see that you don't notice that lag, that delay. And that's mainly because you're now reading things off of your SRAM on your caches and so on. So that's something noticeable that you've probably seen in your everyday life as well. All right, so let's have a quick break here, and I'm going to start talking about caches afterwards. All right. So what we're going to have is, now we're going to start talking about, the actual and specific implementation of our memory hierarchy. We're going to have 3 main, layers. We will have what we call a cache, which we're going to usually show it with a $sign. We're going to have the main memory, which is basically would be our DRAM. And then we're going to have a disk, which is a big, area for storage, but it's really, really slow. Okay. Our cache usually are, divided into an instruction cache and a data cache, because instructions needs to be treated slightly differently than the data. And then we're going to have our registers or register file as kind of on chip, storage units, which is basically our register files, really, really fast, and we talk to them regularly. What we have in modern system is that we don't have one single layer of cache. What we have actually is a multi-level cache. So we have a data cache and an instruction cache. And we usually refer to this as L1 cache or level 1 cache, but we will have level 2 cache and level 3 cache. And in some new systems, we also have level 4 cache. we usually don't have more than 4 levels of cache because the size of the cache grows so significantly that at that point it's not faster than DRAM. Usually the last layer of cache, whether it's third or second or fourth, usually call that last level cache or LLC. So if you heard the word LLC, it means that the last level of cache before actually jumping into the main memory. Depending on the architecture, this LLC could be L1, could be L2, or could be L3, or even L4. Typically, what we are discussing in the class, majority of the systems has 3 levels of caches, and L3 is usually the LLC. Okay. For our L1, L2, and L3, we usually have a distinction between instruction cache and data cache for L1, but we're not going to have a separate instruction cache for L2 and L3. So L2 and L3, or even L4, are all shared among both data and instruction. For first level, for L1, we have a separate instruction cache and separate data cache. We're going to revisit this later in the course, but for now, just have that in mind. Okay. So first of all, let's see why it's so important to have a cache and have a very performant cache. I already discussed this, but let's revisit this one more time. So if you look back when we were talking about our pipeline processor, whether in order or out of order, especially for in order, we had this data memory that it was essentially treated as one element in our pipeline. And we always say that, okay, accessing the DM takes 1 cycle, similar to our ALU, similar to our decoding, and similar to all the other stages, right? In reality, though, what is happening is that depending on whether we are reading it from L1, L2, L3, or DRAM, the time it takes to get that value is significantly different. If we go to our L1 cache, that's when things get 1 cycle, okay? But if we go to the L2 cache, typically we're talking about 20 to 30 cycles. If we go to L3 cache, we are talking about hundreds of cycles. And as I said before, if you go to our main memory, we're talking about 500 to 1,000 cycles, okay? So this idea of all data memory and we go and read things, it only works if we are reading things from our L1 cache. If we go to further stages, then we have to stall our processor for how many cycles? For as many cycles that we need to go and grab that data. And then for in-order processor, this is a huge performance hit because remember, we have to stall the entire processors. We cannot run anything else until this data comes back, and then we can continue, right? So we're talking about stalling a processor for 100 cycles or 1,000 cycles if the data is in other stages of the cache, okay? So it's really, really important to get as much as performance you can from your caches. Okay, so now that we have this in mind, let's talk about how we design our caches. What are those decisions? How do we store data? What is the size, the right size for our caches, and all those things? And remember, the goal is that we want to increase the chances of data being in our L1, then in this next layer in L2, then in next layer in L3, and then hopefully the minimum amount of data needs to be read from the main memory. Remember, we cannot completely eliminate the need from reading from disk or reading from the main memory because just the amount of data that you want to read is big. If the amount of data that you want to read is bigger than the size of the cache, then just you theoretically need to go to your main memory, right? The main memory is there for you to read things. If you don't want your main memory, then there's no point of having it. So at some point, you have to go to that main memory. But what we're arguing is that maybe just ideally that would be just one time. The first time you read that data, you have to go to main memory. After that, if you can maximize the usage of that piece of record, then you're having the best possible memory design that you have. Right? So that's the goal. We want to minimize the stalls. Again, the goal of designing our main our cache system or memory hierarchy system is same as what we did for processors, and that is to improve and maximize our performance, right? So there are two things that we use very frequently. There is a cache hit and a cache miss. For each layer, when we go and grab the data and the data is there, we call it a cache hit. If the data is not there, we call it a cache miss. And for a cache miss, what happens is that, for example, if we go to our L1 cache and see that this is a miss, then we have to go to our L2 cache and search for it. Hopefully it's there in our L2 cache and there will be a hit. If it's not in our L2, then we will incur another miss. We go to L3 and then read it. If it's there, it's a hit in L3. If it's not, we go to our main memory. If it's not in main memory, we go to the disk, and eventually it will be in the disk, right? So if you're really addressing something that you have used before, it will be somewhere. You just have to find it, right? So in each layer, in each level, you're gonna have a cache miss or cache hit for L1, L2, and L3. Okay. So the problem that we have with cache is we have limited space, right? So I said that for L1, we are talking about few kilobytes. Of course, if you have a bigger cache, the chances that we're going to have a more cache hit would have been higher, right? More space, more data, higher chance of hit. But we have a limited space. So what we need to do in order to fix this is what we call a cache management strategy, okay? The cache management strategy is basically this series of decisions that we're going to describe of where to store what, when to get rid of something, when to replace something, and all those things. So there are multiple things that we need to do in our cache management in order to optimize the amount of time that we are going to the cache and reading things. So we want to optimize and maximize the amount of L1 cache hits. We want to then, after that, maximize the L2 cache hits, then maximize L3 cache hits, okay? So that's the goal. In order to measure the performance of the cache, we kind of use a metric that's kind of like similar to what we did for iron law. We usually call it average access time, or AAT. The average access time is a combination of three factors. The hit time plus the miss rate times the miss penalty. So what these things means, so just assume that we only have one level of cache. We have only L1 cache, and we want to see what is the performance of this cache, okay? So in majority of the time, it will be a hit. So the only time it takes for reading the cache would be a hit time, okay? So this miss rate, if this miss rate is equal to 0, then this term kind of cancel each other out. So your average access time is basically your hit time, right? And I said, for example, for L1 cache, this is 1 cycle. For L2 cache, this is 100 cycles or 20 cycles, right? But what happens is that in reality, you won't have 0% miss rate. You will have some miss rate. Hopefully it's small, but there will be some miss rate. So what will happen is that miss rate will be added to your hit time, and not just the miss rate, but times the miss penalty. And miss penalty means the time it takes to bring the data from lower level of the cache. So basically what we're saying is that you want data, two things happen. Either the data is in your L1 cache, and that's your hit time, or the data is not in your L1 cache. So you need to go and grab it from another layer, right? How often do you do that? That's your miss rate. What is the time it takes to go and grab it from the next layer? That's your miss penalty, okay? So adding these things together, that would be the performance of your cache, okay? So if you have multiple level of cache, then what will happen in that case? Then basically your miss penalty becomes a new AAT itself, right? So this is your AAT of your L1 cache, in some sense. This itself becomes the hit rate or hit time of L2 plus the miss rate of L2 times the miss penalty of L2. This miss penalty of L2 itself becomes the hit time of L3 plus the miss rate of L3 times the miss penalty of L3. And this itself is basically the hit time of your DRAM. And then let's stop here and let's assume that there is no disk. So really what your overall 3-layer cache system average access time is your hit time of L1 times your miss rate of L1 times this large, term here, which itself is hit time of L2 plus miss rate of L2 times this statement here, which is hit time of L3 plus the miss rate of L3 times this term here, which basically this is the hit time of your DRAM, okay? So if you just combine these together, you will get your average access time of your multi-stage cache system. Is that clear? So the question is, when we have a miss, what we do is that we go to a lower level and bring in the data. Do we read it from the cache again, or do we read it directly from there? In both cases, you incur that hit time because the hit time is basically the time it takes for searching. Because the first thing is that you don't know whether your data is there or not, right? So you have to go to your L1 first and search. That is your hit time, because if it's there, then you have it. If it's not there, you still paid it the search time, then you see, oh, I don't have it. So you have to go to L2. Again, you have to search through your L2. That is your hit time of L2. The same story for L3 and so on and so forth. Yeah, your hit rate is the time it takes for searching through your cache.
So could you also have the DRAM?
Yes, the question is, why are we doing this? Yes, I mean, in reality, this would have been hit time of DRAM plus miss rate of DRAM plus times the hit rate of disk. As I said, there won't be a miss in disk. So at the end, it would be your disk. Yes. And these times are significantly higher, right? We are talking about 1,000 versus 1. That's the difference. Okay. So let's have a practice example for you guys. Let's see if you can actually find a time for this example. So the key is that you need to find the average access time of your cache first, and that would be the time it takes to access the cache, and then you have to factor that in with your CPI. Okay. So what we're saying is your memory doesn't take one cycle; it takes more. How many? You have to first compute your average access time first. Once you have that, then factor that in with your CPI. And think about this, we only have one level of cache, okay? All right, so what would be your average access time first? It would be your hit time, 1 cycle plus 0.10 as your miss rate times the miss penalty, which is 10. So your average access time is 2. So what does this say is that whenever we have a load, I'm adding an additional cycle to our system, to our design. Okay, so what does this say is that the CPI for R type instruction is 1, the CPI for LW type instruction is 2, and the rest is just an average sum of 30% of 2 plus 70% of 1, right? So that would be your average CPI time, right? So plus times 2 And actually, you have to do first IPC and then do average sum of IPC. So this is half, this is 1. Then you say my IPC is 70% of the time 1 plus 30% of the time 2. So 1 point something, and then make that, reverse of that to your CPI, and that would be the value that you will get for your CPI. You actually have it divided by 2 as well here, right? That would be your average IPC, and then 1 over that would be your CPI. Does that make sense? I just did a weighted sum of my IPCs. I did it divided by 2 because 30% is that, 70% of that divided by 2 is the average number. That would be my average IPC. 1 over IPC is my CPI, and that would be the overall CPI. Does that make sense? All right. Any questions? Are we good? Right? No? Yes? Okay. Okay. So let's talk about the cache management now. And for the cache management, we need to kind of answer a bunch of questions. The first question is how to store data, where to store data, how do we access the cache, how do we find this information in the cache, and so on. So let's start with that. And let's start with what we have and what we want. What we have is a 32-bit address. We're still thinking about RISC-V as our baseline CPU. We are talking about 32-bit addressing. And what we need to do is we need 2 things from our cache management system. We give an address from the CPU side, so we are CPU. We give a 32-bit value, and that is our address. Then this is our cache management or cache. And what we need from the cache is whether this exists in L1 or L1 or not, so yes or no. And then if it does, give me the data, right? I need the data as well, and I need the yes or no. Because if it's not, then I have to go to L2 and do the same thing, and then to L3 and do the same thing, and so on, right? So we need the answer of the existence, and then we need the actual value or the content, okay? So this is the way that we're going to do that. So the address comes in, and it goes into this storage area, which we call tag store, which essentially the tag keep track of what's been stored where. And what we need to do is compare our address with that tag, which I'm going to explain later. And if the answer to this is yes, then we need to go here and actually grab that data. Okay, so we have 2 separate storage within our cache. One is to keep track of what we have stored, and the second is the actual values, right? So basically, kind of like, the indicator or the ID and the actual value. If you remember for BTB, that was exactly what we did with BTB2. We had some tags and we had some data, and we showed that it's basically these 2 together give us what we want. Okay, so you might ask, why do we need tag? And let me start with this simple example of, let's say we have only 3 bits. Okay, the address is 3 bits. And in ideal scenario in our cache, we have 2 to the power of 3 entries in the cache. So we have 8 entries in the cache. In this case, all we need to do is just index this table and bring the data that we want. We don't need to be worried about tags because we don't need any tag. Because for any number of addresses that we have one-to-one mapping exactly to 1 entry in my cache, right? So 0, 0 means A, 0, 1 means B, and so on and so forth. So I know I don't need to keep track of what I've stored where. All I need to do is looking at my address, going into that memory, bringing that value, and that's it. So I don't need this, basically. If I have the same number of entries and with the address that I have. But that means that for a 32 bits, I need 2 to the power of 32 entries in my cache. And as I said, we're talking about kilobytes of cache, which means 2 to the power of 10 or 12 or 13, right? But we have 32-bit address. And we want to use this 32-bit address to address that 2 to the power of 12 entries, okay? And that's where we need tags to kind of like, keep track of where is stored where. So when going to the same examples that I gave you, let's substitute this 8-entry table with a 4-entry table. And now we have still our 3-bit address. But the problem that we have now is only 2 bits is used for addressing this, okay? So I need a mechanism to kind of like saying that, okay, what do I store where? And given that I have 8 different possibilities and 4 different entries, for each entry, there will be a collision. There will be at least 2 entries that goes into the same line, right? So I need to kind of come up with a strategy that I can keep track of this, right? So what I can do, I can say that, okay, I'm going to use this lower 2 bits to address this cache, and I'm going to call that index, okay? And since this is a 3-bit address, whatever remains because what I call tag, and what I'm going to store is this tag into additional storage area called a tag store. And this tag store is basically needs to just save 1 bit, right? It needs to store 1 bit, 0 or 1. So for example, if my index is 0, 0, and the tag that I store is 1, this means that I have stored 1, 0, 0, or I stored E, right? If I stored 0 in my tag, index 0, 0 plus the tag becomes 0, 0, 0, it means that I stored this, right? So that the idea of the tag is for you to give you this indication of what we have stored in that, okay? And the number of tag bits is basically the number of address minus the number of index bits you have. And the index bit is basically the number of entries you have in your cache. If you have a cache that only 1 kilobyte, then you have 2 to the power of 10 entries. It means you only need 10 bits for your index. So if you have a 32-bit address, 32 minus 10, you will have 22 bits for your tag. So you need to store 22 bits in your tag store for every entry to know which address you have stored. Okay, and remember, this is on top of your actual 32-bit storage area for your data, right? So if I go back, we need this to keep track of what we have stored, but we also need this to kind of like store the actual value. So this will only give us the answer that whether we are storing 0, 0, 0 or 1, 0, 0, for example, right? What exactly are we storing there? This is still a 32-bit value, right? Or whatever size that we are talking about. It's a 1 byte or whatever it is. So we'll talk about that, okay? So don't mix the tag store with data store. Still need data store, and your data store is still 32-bit or whatever size that your data should be. The tag store is something specific because of the way that you're organizing your cache, and mainly because you don't have enough entries in your cache, because you want to keep track of all the addresses that you have stored, because you don't want to read something incorrectly, right? So that's the idea of having a tag store and the size for your tag store. Is that clear? Any questions?
Curious as to why we choose the rightmost. Is it to avoid collisions from like nearby?
So the question is why we are picking this index as the rightmost, and why maybe like not using it this way. This is a great question, and we're going to revisit this, but this is mainly for spatial locality, because we're going to say that if you're accessing X, very likely we're going to access X1 and X2 and X3 and so on afterwards. So it's better to assign X1 to one line and assign X plus 1 to another line and X plus 2 to another line, okay? So if you're actually distinguishing this between them in lower bits, you're basically it's guaranteed that this is going to be one line, separate line, separate line. For example, if I did it this way in higher bits, then all these would have been assigned to the same line. So they're kicking each other out, and I get lots of performance mess because of that. But we will talk about those actually. All right, so this is our tag, and this is our data source. So essentially inside our data store, that's where we actually store these values, okay? Okay, so now that we know this, there is two main, ways of we can kind of organize this our tags in our data store. The first one is, let's say we have an available table. One thing we can do is that we don't care about the index. What we're gonna do is that we say that there's an equal chance of your data to be in any of these entries. All you need to do is just find the first empty spot and save it there, okay? So what I would do is I basically get rid of this index, just treat everything as a 3-bit tag, and I'm going to say that, I won't have this. Here, I'm going to store 3 bits values. And the way that I'm going to store these things is, if a new data comes in, I'm going to go and find the first empty spot, and I'm going to put that data there. The next time the next address is, I'm going to just compare it with all these different entries and see if there's a match between the tag of mine and the tag that's been stored. Okay, that's one way of storing this. The second way of doing this is what we discussed here, that we use index and saying that, okay, I'm going to have a predefined specific rule for knowing which address goes to where. For example, in this case, I say the lower 2 bits will be used for index. So if this lower bits is 0, 0, I know exactly where I'm going in my tag store. I'm going to the index 0, 0. If it's 0, 1, I'm going to 0, 1. So I know exactly where I go. The data is either there or it's not there. There is no other way of this data is stored somewhere else, okay? So these are two ways of thinking about this. And there is pros and cons for each one. Anybody wants to volunteer? What's the problem with the first one? Potential challenge for the first one, where we basically don't care where we store. Whenever we have any data, we just go and put it there, and next time that something comes in, we just search through our cache. What's the problem with this one? Yes, so the problem is that the search time takes much higher, right? You have to search through the entire cache because you have no idea where this data is stored. It could be on line 1, on line 2, on line 3. But what's the benefit of this? Like, why this would be a good idea? What's that? It's, someone says it's fast writing. It's actually not fast, but it's any other idea? Yeah, exactly. You use your storage area the most efficient way, because you're just finding the first available spot and you just put your data there. Versus on the second one, it's the exact opposite of this thing. It's much more faster to read from it because you exactly know where to go and look at. So your read time, your search time is minimal, because all you need to do is just go into this first line and grab it if it's there. But on the other hand, assuming that, for example, you have a sequence of addresses that all maps into the first one, even if you have empty spaces here, you cannot, utilize this empty spaces because your addressing tells you to just write things here. So if you have A1, A2, A3, these different addresses that all happens to map into index 0, 0, you will save A1 here first. Then A2 comes and A2 wants to write into the same spot. So what will happen is that A2 needs to kick out, or what we call evict A1, and replace it with A2. Then A3 comes and then evict A2 and put A3. And then if the next time A1 comes, you'll see that A1 is no longer there. Versus we had 4 available spots, so A1, A2, and A3, all of them could have been into this cache if we have used the first opportunity, right? So we are dealing with this trade-off of, on one hand, we really want to use all these available spots as efficiently as possible, but the search becomes a huge pain for us, because then we don't have any idea where this is stored, right? So we need another cache of that cache to keep track of these things, which doesn't make sense, right? And of course, this solution might, sit somewhere between those two, and that's what we're going to describe in both of them. But let's first talk about this first, the B version. Let's see how we actually implement that. See how we can optimize that, and then we're going to go to the A, and then we're going to go to the hybrid solutions that has A and B both in the same time. Okay. So the one that we basically assign each row to a specific index, we call that direct map cache. The name is basically suggesting that you're directly mapping your cache into a specific row. So think about this as your this is your memory, and this is your cache. Your memory is much bigger than your cache. So what will happen is that if you want to store things from your memory to your cache, there will be scenarios, for example, this grayish lines, that all of them have the same index, right? Same index, but they have different addresses. The uppermost 2 bits are different, but the lower 3 bits are the same. So all of them are mapped into this 001 index. And the same thing for the blue one. So 101, 101, 101, which is mapped into this, right? So we call this direct map cache. We basically take a look at these the lowest bits as the index. How many index that we have depends on how many entries that we have in our cache. And then we store the rest as a tag into those entries. And that's very simple, and we call that a direct map cache. Let's talk about how we actually can now improve this before actually jumping into the different strategies for storing things. So the first thing that we usually do in our direct map cache is, instead of like storing just 1 byte or 4 byte of data, we store much bigger information in one cell. The reason for that is that, remember I told you that we're going to have spatial locality, that if we're going to use X1, it's very likely that I'm going to read X2 and X3 and X4 and so on as well. So what I can do is that, remember I told you that, we have 32 4 bytes, and then we have 1 byte in memory and so on. We can have another way of, even confusing you more, and have what we call a cell or a block, which is essentially a combination of bunch of bytes together, and that would be one cache line. So whenever we are reading from cache, we're just not bringing 1 byte, we are bringing 64 bytes together, and that would be what we're reading from the cache. The reason is, again here, that if your first byte is X1, then your second byte would be X2, your third byte would be X3, and so on and so forth. And 64, for some, implementation and feasible reasons, we pick 64. But what we are doing is that we are basically, making a bundle of these instructions, memories units together, and save that into one cache. Okay. So when you say cache block, means that combination of multiple bytes, and usually we are talking about 64 bytes for the cache block. Okay. So again, going back to this confusing terminologies, for CPU things, we're assuming that things are byte addressable, right? So we're thinking about the memory as this byte addressable array that we can access each byte together. From our CPU side, we do addresses 32 by 32, but we said that when we send this to the memory internally, write and read things into byte chunks. Like you basically combine 4 bytes together, and that would be one read of memory or one write to the memory. For caches, this is even more complicated, because now we are introducing the notion of blocks, and blocks is bigger than 32. It's usually 64 bytes. So it's not, so 32 is 4 bytes, and we are saying that we are basically doing 64 bytes. So what we are doing is, for each read from the cache, what we are bringing is that we are bringing address plus 1, address plus 2, all the way to address plus 63. So we are bringing all of them together as one block of the cache. The reason for that is for the locality. Okay. But from now, the terminology I'm going to use in my lecture, in this lecture and next few lectures, that when I'm talking about the cache and when I'm talking about the addresses, I'm talking about the addresses after the shift and all these things happen. So when I say this line and next line, I'm talking about two consecutive lines in the cache domain. In the processor and CPU domain, that would be address and address plus 64 and plus 64 and plus 64. Okay, so don't be confused when you're using this terminology. If you're doing byte addressable, each consecutive blocks are 64 bytes away from each other. Does that make sense? Bytes. Okay, so we have some terminologies that you need to kind of learn. We have this notion of cache block that I just described. We also use interchangeably block and line together. So when we are saying a cache line, we mean one block of the cache. As I said, it's usually 64. The cache set is a combination of lines or blocks. For direct map cache, for example, cache block, cache line, and cache set is the same thing. Once we introduce others, you will see that there is a difference between set and block. We have the notion of the tag. Actually, as I said, the tag is a part of the address that is used to figure out whether or not we are storing things or not. Depending on how we are, creating our cache, this tag could be a few bits or could be more bits, right? And then finally, we have this notion of what we call a valid bit. That valid bit is basically this auxiliary or this flag bits that we usually have for every cache line to just tell you that this is a valid line that coming from the process, coming from the memory, or this is an old line that we need to discard. We no longer need it. I'll describe why we need a valid bit very soon, but just generally have this idea that there might be additional flag bits as well in our systems. Okay. We're doing good time. Okay, so let's say, for example, we have a 4 kilobytes of cache, and let's say we have 4 bytes of data, and we have a 32-bit addresses, and we have 1 block per set. Okay, so here what I'm doing is that I'm saying that my blocks are 4 bytes. My data is 32 of 4 bytes. Okay, so for this, let's see if we can actually figure out what is the width, what is the lines, what is the number of sets, what is the index, and what is the tag size. Okay, so first of all, let's start with something simpler. So we say that the cache is 4 kilobytes. Okay, so 4 kilobytes means that we have 2 to the power of 12 entries in my cache, each 1 byte, right? Okay, so the addresses to access this cache is 12, the first 12 bits of my address, right? For now, let's assume that each block is 1 byte, and then I'm gonna go to the 64 bytes and see what changed. Okay. So if you're doing that, then we're basically saying that my tag size would be 32 minus 12, or 20 bits, right? And this 20 bits would be the size of each entry for my tag. And what would I need is, for every entry here, I need a tag for that, right? So I need 20 bits times 2 to the power of 12, and that would be the storage that I need for my tag store. Okay, so I have 2 to the power of 12 entries. Each entry I need 20 bits for my tag, so I need 20 times 2 to the power of 12. That is just for storing my tags. Okay. So the tag size or tag store is this many. Is that clear? Okay. How many index do I need? I need 12 bits of index. How do I come up with the 12 bits? I just took this value, and that's how I came up with 2 to the power of 12. Okay. So 12 is this. For direct map, as I said, sets and blocks are the same thing. So the number of sets is basically the number of lines that I have. Similar to the previous case, is 2 to the power of 12. Cache lines and sets are the same things for the for my direct map cache. And the width that I'm going to have, remember, the width for your data store is always 32 bits if you're storing 32 bits. If you're storing 64 bytes, it would be 64 bytes. Whatever number that it says as your basic block, that would be the number of bits, okay? So for example, in this case, if you say that if I redo this example this time, so for this, I just assume that this is 1 byte, okay? So my width is 8 bits. But if I want to do this correctly, what I should have done is, if I assume that my cache lines are 64 bytes, then each block would be 64 bytes. So the number of entries is 4 kilobytes divided by 64 bytes, okay? So what I would get is 2 to the power of 12 divided by 2 to the power of 6. I get 2 to the power of 6 entries, okay? Remember, the thing that changed now is now each line, each block is 64 bytes and not 1 byte. So that's why the number of entries shrink down from 2 to the power of 12 to 2 to the power of 6, okay? So now my index bits is basically 6. I need only 6 bits for my index. As a result, my tag size grows significantly because now I need 32 minus 6, which is 26 as my tag size per tag. And I have 2 to the power of 6 times 26 as my tag store. Any question why we have this? Actually, so the question is why your tag size increase? Actually, our tag size decrease, right? Because you have less entries. Although your tag per tag is bigger, the entire tag store is smaller. But the reason that your tag size is increased per entry is your address is still 32, right? The number of index changed from 12 to 6. So if you go way back here, if my addresses are, for example, 6 bits and my number of index is 3, then 6 minus 3 is the size of the tag. If I only have 2 indices, then that would be 4, right? That's a good question. So someone said, so the question is, if the addresses is in bytes, then yes, that will happen. Here, I just assume that the addresses are like each address is accessing 1 cache block. So if the addresses are coming from the CPU, then you will say, if I add more things as 1 cache block, then the first 6 bits is kind of removed for that. We're going to actually get to that part. But for now, I'm just assuming that 32 is the address within the cache. And then that's why I need 6 plus that number. Does that make sense? Any other questions? Okay, I guess I can pause here. Let me just finish this and then we can move on. So the cache lookup or the process of looking for the data would be something like this. So let's say we have an 8-bit data for our direct map. And then let's say we have 8 entries in our direct map cache. So we reserve the first 3 bits for my index. Since I have 8-bit address, 8 minus 3, 5 is the number of tags. So each of these is 5-bit. What I will do is that in order to see whether this data exists in my cache or not, I'm going to use this index. For example, if my index is equal to 111, I go to the last entry here. I'm going to bring this tag and compare this tag with this tag that I have in the address. If these two matches, it means that I have stored the correct address. So this would be a hit. And if it's a hit, then I'm going to my data store, same index, I'm going to bring my data. And now I have the answer to hit or miss. And I also have the data that I want to read. Does that make sense? And the interesting thing is, we don't need to wait for this to read this. We read these two in parallel. And what we really do is basically, this would be our data memory. We read this, we add a mux here, and this mux would be basically garbage and this value. And if it's 0, we read garbage. If it's 1, we read this value here. And 1 means hit, and 0 means garbage, means miss. Does that make sense? So we're not waiting for we don't serialize this. We read both at the same time. So that's our lookup and our reading happens exactly at the same amount of time. That's why the hit time is basically our search time. If our search time is fast, our hit time is also fast. Okay? All right. So talk about the rest, the alternative to direct maps next time. Okay?